So before we do this next question, number 4, we have to note that it's important to know how the wording is going to affect a vector diagram. So for example, here's the same speed, a 10 kilometer per hour wind is blowing at or toward a bearing of 200 degrees with direction, and a 10 kilometer per hour wind is blowing from a bearing of 200 degrees. So how is that different between them? So first, let's draw our vector. So I have, let me just change my color here. So if all it says is 200 degrees, then that must be a true bearing, right? So starting with north here, and let me just draw a vector. And then again, if it was going up to here would be 90, another 90, 180, 270 would be too much. So if I go back to 180, the difference between 200 and 180 is 20 degrees more. So let's say something relatively like that. And then I would draw in that from north clockwise, that degree is 200. Okay. And then the 10 kilometer per hour wind, I could write here again, 10, I'll try to write it sideways, kilometers per hour. Yeah, I think you get the point. That's a 10, just try to write it better than I did. And our scale, because it's not going to be 10 centimeters, let's do 1 centimeter equaling 5 kilometers per hour. So then therefore, if this is 10, this should be 2 kilometers long, 2 centimeters long, 2 centimeters long, right? That looks a little bit longer than that. So again, if you want to draw it accurately, just use a ruler. Now, if it is blowing at or toward a bearing of 200 degrees, this is at or toward. Nothing changes about this diagram. Whereas if I relate it to this side here, a 10 kilometer wind, everything's the same as blowing. The only difference is the wording here from a bearing of 200 degrees. Let's go ahead and draw in that 200 degrees again. Right? So that 200 degrees, I'll just draw that angle in. 200 degrees and my 10 kilometers per hour. Now, when I'm going from a bearing of 200 degrees, it's going in the opposite direction. It's coming from this direction here and continuing on this way. So what I want to do is extend my vector and basically draw in an opposite vector, right? Going in this, let me just put, basically this would be the tail and this would be the head coming in this direction, but we don't want the head. It's not correct to have the head like going towards and touching the origin or starting at the origin, let's say. So what we're going to do is we're just going to bring kind of the tail forward and again, just extend it. So going in this direction here. So again, if I went all the way around here, this would be 90 degrees, right? This is 180 degrees. And then to get from 180 to 200, I was drawing in an extra 20 degrees, which means that this angle here, due to opposite angle theorem, right, would be this angle here would also be 20 degrees. So another way that we could write this is just down below here, a 10 kilometer per hour wind is blowing at a bearing of 20 degrees. So when it says at, right, or toward, just like this says at, and this says at, it's exactly the way the angle is said, starting at north and going clockwise. This was starting at north and going clockwise, 20 degrees, right? But when it says from, then it's going in, let's say, the opposite direction. So you would draw your, let's say the best thing to do would be draw your vector the way you normally would if it was at or toward, and then know that if it's coming from, it's going in the opposite direction. And then figure out what that bearing would be, what that angle would be. You don't have to rewrite it depending on if the question asks you to or not, but those are the differences in the wording there. So now looking at number 4. Hopefully that's enough. I might bring it up after I read it. I might move it up because I think I need a little bit more room, just so you guys know as well. A 25 Newton traffic light, right? So that's the force hanging down at an intersection, is hanging from 2 wires that are at an angle of 35 degrees and 43 degrees below the horizontal. So basically, again, like a grade 10 question, from the horizontal down, right? And from the horizontal down. A, what is the equilibriant vector? What is the resultant vector? And what are the tension in the wires? So basically 35 and 43 degrees are already in the diagram. The only thing that we don't have in the diagram is the 2,500 newtons of force. So if I move this up, I'll add that in on my own just to have some more room again. So the equilibriant vector, right, is the force that keeps the wires from moving. What is keeping the traffic light still? So that is 2,500 newtons downwards. That is making the whole situation, or in this case, the traffic light, not move. So if I draw in that vector, let's use light. Hopefully you guys can see that color. So this force where the 2 wires meet coming down, okay, that force there at 2,500 newtons would be my equilibriant vector. So let's just write in here, 2,500 newtons downwards is what's allowing the traffic light not to sway too much. It's going to a little bit, right? But it's what's keeping it down. What is the resultant vector? So again, we learned that the resultant vector is just the opposite of the equilibriant vector. So let's write that down. Opposite of the equilibriant force. And so that would be, the opposite would be 2,500 newtons upwards. And I can draw that in opposite this vector here. So again, going up to the vertical would be this one here. And this is my resultant, R vector, resultant vector. Okay. What are the tensions in the wires? So this is where we need to pay attention here. So it's asking us to figure out what the tension is of, let's say, the left side wire and what the tension is in the right side wire. So I want you guys to think about this. You probably know this, but just you might need to take a second just thinking about it, depending on the last time you've actually had this kind of example in real life. In terms of tension, I mean, not in terms of the traffic light, obviously. If I have a shorter wire, so for example, this wire looks shorter, and then this one obviously is the longer wire. I want you to imagine kind of holding this wire in your hand and kind of flicking it, or just kind of feeling how the tautness of it, right? As opposed to this wire here. This one would actually be tighter, right? This one would actually have a stronger force, and it wouldn't sway as much. The longer the wire is, right, the lesser the force. And if you think about it, once it gets so long, this wire is going to sway a little bit more, right? So it has less force. So when we go to draw this, if you look, I don't have any, I don't have any quadrant bearings. I don't have any direction given in terms of the wires here. If I were to draw a horizontal line, just coming from here, let's say, draw a horizontal line. This one, I'm going to erase that one. I'm not quite at the origin there. Try a bit better. And do a horizontal line. Then we know that if we said this is from the horizontal down, it said in the question, and this is also the horizon, the horizontal, then we can use a Z pattern. And therefore with the Z pattern, we can say that this angle here is 43 degrees, right? And with Z pattern, we can say that this inside angle here is 35 degrees. Okay, so when I do my diagram though, I'm gonna do my draw my north, south, west, east to begin my diagram. And I'm going to draw one, let's say we call this wire T1 or T1 vector, and let's say we call the longer wire T2. Okay, because it does have a force and it does have a direction. So to draw in my vectors, I am going to be from the horizontal. So starting east, let's say from the horizontal, I can go up 43 degrees and draw in that wire. Now, to draw in the wire, since I don't have like a force on this wire, I only have the resultant force, right, up and down, and the equilibrium force. And I don't have a force here. That's what I'm trying to figure out, is the tension would be the force on the wires. How do I know how long to draw it in terms of a scale and everything? So what I'm going to do is actually the opposite of what's in the drawing. This drawing has a longer wire here and a shorter wire here. But what are our vectors going to be? Our vectors represent force, right? So which one has the more force, the greater force? Didn't we say that the shorter wire, right, is more taut, has the greater force, the stronger force? So I'm going to actually draw this one longer, and hopefully you understand that. So up from the horizontal, I'm going to go 43 degrees, which is basically, let's say diagonal, right? 45 degrees basically. And I'm going to draw that one a little bit longer like that. And I'm going to call that one T1 vector T1, wire T1. And then for my other vector, right, this was longer, it has less force, it has more sway to it, and it's at 35 degrees from, let's say, the west, from the left horizontal up. I'm at 35 degrees, so not quite as much of a diagonal, more like that, let's say, and make sure that it's a bit shorter. There's no actual like magnitude given as to how much, but just make sure it's shorter to say that it's actually the less stronger force, has the lesser force. And then let's draw in our angles. So this would be our 43 degrees. Make sure you get that right and you don't mess up the 43 with the 5 from the 35, and the 35 degrees is in here, right? That's from the original. And we should call this one T2. I'm just T2. So now let's finish our parallelogram here and join them together. Okay, and we're not sure if these are 90, but I'm looking down here at the horizontal and I can figure out what that angle is actually. Because if you look, this horizontal here, horizontal line would be 180 degrees, right? So just here, if I took 180 degrees and I have this portion minus 35 minus this portion 43, then that would tell us what this whole inside angle is, which would be helpful. So 180 minus 35 minus 43 is 102. So I guess the point is that it's not 90. So that helps us with if I can use Pythagorean or if I can use trig ratios, right? If I have to use sine law or cosine law. So if that's 102, that means that this entire angle here would be 102. But what I'm needing to know is to extend my, just going to extend this. Do I have a straight line? Yeah, I'm just going to extend this up. Yeah, this isn't, I'm going to have to adjust this because the corner here should be on my resultant vector, this corner. So I'm off a bit here from my drawing. So I think it needs to be a little bit shorter. So I'm just going to adjust this. Because again, I don't have a triangle here on this side, right? So in case that happens to you, because again, I'm not measuring with a ruler using this recording software. So if I make this one a little bit shorter, I think I just have to redraw it. Let's try to get that in there better. That looks diagonal to me. And maybe this one has to be shorter too. If I go up like that and come over, or I can kind of make it work here without having to redraw more. So if I go up into the corner here, and then I come up like that, that's how we want it to be. So that your resultant vector is the other corner here. Okay, so then what other angles do I know? What other information do I know? That's my resultant vector. I can put that in red just to kind of show you. These are my two vectors. The resultant vector is again tail to tail method where the tails meet and coming up there. Resultant vector R. And that has a force of 2,500 newtons. We don't need to state whether it's upwards or downwards, right, within the diagram, but we can just say that the force there is 2,500 and that number will help us. So I have this side. I don't have this side. I don't have this side. This side is T2, tension 2, but I don't, the vector as well. This side is T1 vector, but I don't have the sides. Do I have any angles? I don't have, if this is 90, this was going directly upward, right? North, the resultant vector, and this is east. So I could also take 90 degrees and minus 43 to get this inside the right side angle in here, right? So 90 minus 43 is just this portion here is 47. Okay, so if I wanted to pick, I'm getting this one, I don't have to get, remember how I can pick which triangle I want, right? So I don't have to get this angle then. If I already have this one, I can just say, okay, I'm gonna pick this triangle on the right. What other angles can I figure out? Remember, I have this whole corner of the parallelogram 102. So this whole corner here, based on supplementary angle theorem, right, would be 180 minus my 102, which gives me 78 degrees. So this angle inside here is 78 degrees. And then if I have this corner 47 and this corner 78, then this corner here, again, three angles add up to 180. I could take 180 minus the 78 and minus the 47, and I would get an angle of inside here is 55 degrees. So, okay, I've managed to figure out, so that's angle sum of a triangle theorem. I've managed to figure out all three angles and I have one side, right? So if I have all three angles on one side, I have a full set in terms of like if this was angle A, I have a side and an angle, which means that I could use sine law. I don't see any 90 degrees, like I said, so I can't use Pythagorean theorem or primary trig to solve. So what am I trying to solve for? Let's say it doesn't matter if it's T1 or T2 because T2 is in this triangle as well, right? This side here is tension 2. So either one, it doesn't matter which one I pick out first. So I'm going to use sine law. You can write down, I explained why, because we don't have any 90 degrees. And I have, this is my only side, so I have to use 2,500. So if I put the side on top, 2,500 is associated with the sine of what angle? Sine of 78, hopefully you saw that, opposites, right? 2,500 over the sine of its matching angle, sine of 78. It's up to you what you want to pick first. So let's say, for sake of order, side T1, vector T1 over its opposite would be the sine of 55. And then cross multiplying. Again, this would be the number, right? That's on top, so that comes out in front. T1 vector times sine of 78 is equal to the number 2,500 times the sine of 55. and I divide that by the sine of 78, divide by the sine of 78. And so my T1 vector is equal to, again, if you can do this all as one step on your calculator, that would be great. I have 2093.6, and the vector, we're talking about tension, we're talking about the force of the wire, and up above we were in newtons, right? Because we had the 2500 listed in newtons as my force. So that's one side. Now to get the other side, the longer wire, which has the lesser force, which is again this top part here of our triangle. Again, go with what's given first. So I had the 2500 and the 78 given to me. So I would go with that one again, 2500 over sine of 78. Those are all correct. And then if I want to solve for side T2, then I have angle 47 associated with that, right? So then I would have vector 2 over the sine of angle 47. So same thing, 2500 times the sine of 47. And again, on this side, I would have equal to vector T2 multiplied by sine of 78, but then I would divide by sine of 78, right? So I'm just gonna skip that step and divide by sine of 78 on that side, just to save a step. So the second wire, the vector of the second wire, the force on it would be, what do you have for that? I have 1,869.2 newtons. And now I want to go back to what I was talking about before, about the original question. So we said that the shorter wire had more force, right? More tension. So again, T1, I want you to take a look at, has over 2,000 newtons of force. T2, the longer wire, has only 1,869 newtons of force. So just in comparison, this one has more of a force. It's swaying less. It has less give than the other wire does, right? So our numbers actually confirm that. And then I don't really have room. I could put a therefore statement here, but just saying, go back to the original question. So just part C, right? 4C, what are the tensions in the wires? Therefore, the tension of, vector T1 is 2093.6 newtons, and the tension of wire vector T2 is 1,869.2 newtons.